Packet Coalescence engine is a network buffering subsystem designed to aggregate fragmented IP datagrams into contiguous memory regions. The system maintains an internal queue of arrival timestamps and payload boundaries. Processing occurs asynchronously on dedicated hardware threads. Default coalescence window is set to 8 milliseconds. When the window expires, buffered segments are merged into a single datagram structure regardless of fill state. No special configuration is required for basic operation. Segment arrival is tracked through a monotonically increasing sequence number field embedded in each packet header. The engine maintains a bitmap of received offsets within the current window. Gaps in the sequence space are identified during merge operations. The system does not perform gap filling or retransmission, it only consolidates what has been received. Maximum coalescence window size is 65,536 bytes. Packets exceeding this threshold bypass the coalescence pipeline entirely and proceed directly to the application layer. The internal data structure is a ring buffer with fixed entry count. Each entry contains a timestamp, segment length, and pointer to payload storage. When the ring reaches capacity, no new segments are accepted until the current window is flushed. This blocking behavior prevents memory exhaustion in scenarios with high packet arrival rates. The default ring capacity is 1024 entries. Overflow conditions increment a counter, but do not generate error signals to the calling interface. Memory allocation for payload buffers follows a power of 2 sizing strategy. Requests are rounded up to the nearest supported size: 256, 512, 1024, 2048, 4096, 8192, or 16384 bytes. Allocator maintains separate free lists for each size class. Fragmentation is measured at runtime, but does not trigger automatic defragmentation. The allocator is non-blocking and thread-safe through atomic compare and swap operations on freelist heads. Window expiration triggers a flush operation that merges all buffered segments into a single contiguous output packet. Merging does not reorder segments. Segments are combined in arrival order. Timestamps from individual packets are discarded. The output packet receives a new timestamp at merge completion. Output packets are placed into an egress queue. Queue depth is monitored but does not impose backpressure on the input side. The egress queue operates with first in first out ordering. Each enqueued item maintains a pointer to its underlying buffer and the total byte count. Consumer threads dequeue items and pass them to the application protocol handler. The queue is bounded to 4096 entries. When the queue reaches capacity, the oldest buffered window is immediately flushed to make room for incoming packets. This behavior may result in suboptimal coalescence ratios during sustained high throughput. Coalescence metrics are exported through a standard statistics interface. Counters include total packets received, total packets merged, total windows flushed, and current queue depth. A gauge indicates the number of segments waiting in the current window. Histogram buckets track distribution of coalescence ratios in increments of 10%. These metrics are sampled at 1-second intervals and are available for external monitoring systems to consume. Configuration of the system is performed through a single initialization function that accepts a structure containing all tunable parameters. The window duration, ring capacity, queue depth, and payload buffer pool sizes can be specified. If a parameter is set to 0, the built-in default value is used. Invalid parameter combinations are silently corrected to the nearest valid state. No error code is returned from initialization. Validation occurs during startup and is logged to the system journal. The coalescence engine maintains internal state that persists for the lifetime of the process. State includes the current window fill level, ring buffer contents, free list structures, and egress queue contents. Serialization of state to disk is not supported. In the event of process termination, all buffered packets are discarded. Graceful shutdown should be initiated through a dedicated shutdown function that flushes all windows and clears all queues before returning. Thread safety guarantees are provided for all public functions. The implementation uses reader-writer locks for statistics access and atomic operations for queue manipulation. Multiple producer threads may call the packet arrival function concurrently. A single consumer thread should be used for dequeue operations to maintain ordering guarantees. If multiple consumers are required, external synchronization must be applied by the caller. No deadlock conditions exist within the engine itself. Error conditions within the coalescence engine are minimal. Invalid packet headers are silently ignored and do not increment any counters. Memory allocation failures result in the engine attempting to flush a window immediately. If flushing creates sufficient space, the allocation is retried. If space remains insufficient, the packet is dropped and a counter is incremented. The engine does not propagate allocation errors to the caller through any signal mechanism. Performance considerations for the Coalescence engine include the trade-off between window duration and latency. Longer windows increase coalescence efficiency, but introduce additional delay before packets reach the application. Shorter windows reduce latency, but may result in more frequent flushing and lower coalescence ratios. The optimal window duration depends on the characteristics of the network traffic and the application requirements. No automatic tuning mechanism adjusts this parameter during operation. The payload buffer pool is pre-allocated during initialization based on the configured pool sizes for each size class. No additional allocations occur during normal operation. If the pool becomes depleted, the engine attempts to reclaim memory by flushing windows and returning buffers to the free lists. This process may cause temporary delays in packet processing. The pool size should be configured based on expected peak throughput and average coalescence window fill ratios. Interaction with the network stack is handled through a standard device driver interface. Packets are delivered to the Coalescence engine through a callback function invoked by the network hardware interrupt handler. This callback is non-blocking and has strict latency requirements. The callback enqueues the packet into a work queue and returns immediately. Processing occurs asynchronously on dedicated kernel threads to avoid blocking interrupt handling. The Coalescence engine is designed to operate transparently to applications. Applications interface with the standard socket layer unchanged. All coalescence behavior is internal to the network stack and is not exposed through any application programming interface. This design choice ensures compatibility with existing applications and eliminates the need for application-level modifications. Maintenance and monitoring of the Coalescence engine should be performed through the exported statistics interface. Regular examination of coalescence ratios and queue depth provides insight into system performance. If coalescence ratios are consistently low, the window duration should be increased. If egress queue depth approaches capacity, the queue size should be increased or application consumer throughput should be improved. These adjustments require process restart to take effect.